Quantum physics has a mistake of being complicated and hard to understand. In fact, Richard Feynman, who won the Nobel Prize for his work on quantum electrodynamics, once said, "If you think you understand quantum physics, you don't understand quantum physics." Which is kind of disheartening for us, because if he didn't understand it, what chance do the rest of us have? Fortunately, this quote is a little misleading. We do in fact understand quantum physics really well. So in this video, I'm gonna talk about how quantum physics came into light, how does it works, and most important, usefulness of quantum physics. So without wasting time, let's get started. This all started in the year 1801, when famous physicist Thomas Young performed his famous groundbreaking Young's double-slit experiment. In his experiment, Young sent a monochromatic light ray from a single source, directed towards a barrier with two closely spaced narrow slits. The light passes through the slits and strikes a screen on the other side, creating an alternating bright and dark bands of light on the screen. This pattern is known as interference pattern, resulting from the superposition of waves. Here, light from single source separates into two coherent sources of light and superpose on each other on the screen. Wherever these source lights are in phase, they create bright bands or maxima on the screen. And wherever they're out of phase, these two secondary source lights create dark band or minima. This experiment proves that light is wave, and you can understand it, because if light isn't wave, then it can never produce superposition alternating dark and bright pattern on the screen. Superposition is only possible among waves. But the funny part is that we all know that electrons are particles, not waves. But if you perform double-slit experiment with electrons, they will give the same result. At the site of maxima, there will be a large deposition of electrons, and at minima, there will be very less or quite negligible number of electrons. So does it mean that electrons are also waves? Later, back in 1887, famous physicist Henry Hertz performed his famous photoelectric effect experiment. The photoelectric effect is a phenomena where light striking a material surface can eject electrons from the material and produce photocurrent. Very simple, but there were some outcomes of this experiment which didn't allow physicists to recognize light as wave. The velocities of the emitted photoelectrons were proportional to the frequency of incident light, and also the process of emission is instantaneous with no time lag between the illumination of the surface and the emission of electrons. Now, if light is wave, then their velocities of electrons should not depend on frequency of radiation instead of intensity of incident light. Also, electrons need longer time to absorb energy of incident light wave, so there might have some time lag. So to solve these problems, there came Sir Albert Einstein in 1905 and proposed that light isn't wave, instead they're particles, and named it photon. Previously, Max Planck suggested that energy of one photon should be h nu, where nu is the frequency of light and h is Planck's constant. But his idea was that in space it propagates as electromagnetic waves. But according to Einstein, light is not only emitted or absorbed in quanta, but also propagates in quanta and not like a wave. Light thus spreads out from the source as a series of concentrated energy packets or quanta with energy h nu. So now if you use Einstein's hypothesis to solve photoelectric effect, then you would get that as energy of photon depends on its frequency, thus the velocity of outcoming electrons will be proportional to frequency of incident light rays. Also, as light is acting as particles, not waves, then there would be no time lag to absorb the energy of incident photon. Now we can conclude that in double-slit experiment light behaves as waves, but in photoelectric effect it seems to be like particles. Also, we know that electrons are particles, but in double-slit experiment they behave as waves. Actually, in microscopic world, elementary particles like electrons, proton, neutron has both particle and wave nature. Also, waves have both wave and particle nature. This is called particle-wave duality. Also, the energy of these particle waves are exactly h nu, not more or less. Here is the difference between classical and quantum physics. In classical physics, wave can have energy from 0 to infinity, but in quantum physics, their energy is quanta, which is h nu. There are other experiments too which stand for particle-wave duality. Like in Compton effect, it shows the particle nature of X-rays, and in Davidson-Germer experiment, it is shown that electrons have wave nature. Now as particles are waves, then these waves should have some wavelength too. This wavelength was suggested by de Broglie in 1924. The wavelength of particle waves is equal to h by p, where h is Planck's constant and p is momentum. For large and heavy objects, momentum is so massive that their wavelengths are too small and invisible. That means that you also have a wavelength, but it is so small that your particle nature is only visible from outside. Finally, after all this, there appeared Sir Erwin Schrödinger with his famous Schrödinger equation in the year 1926. Schrödinger equation is the most powerful equation in quantum physics. It can solve literally everything in quantum physics. Here psi is the wave function of particle wave. Actually, Schrödinger equation is such a huge topic that it can't be covered in a single video. So if you want a separate video on Schrödinger equation, then write down in the comment, "We want it, baby," and subscribe right now. So you can say that quantum physics is only applicable in microscopic world, where everything is so confused that they don't even know what they are actually in reality. Are they waves or particles, or both at the same time? Remember that Schrödinger equation holds equal respect in quantum physics as Newton's law in classical physics. Finally, the most important question is, what is the use of quantum physics? Does it really work? So for your knowledge, quantum theory provides accurate descriptions for many previously unsolved phenomena, such as black body radiation, stability of the orbitals of electrons in atoms, alpha particle emission from nucleus of atoms, also 1D infinite box, and lots of other stuffs that I can't even say. So if you want part 2 of quantum physics, just write down in the comments part 2.